hour can hear you, and you can watch us again if you're interested. So you can say hi to fourth hour.
Hi, fourth hour.
There we go. So hydrogen peroxide reacts with an acidified Okay, so here's my reaction. Hydrogen peroxide reacts with an acidified solution of potassium permanganate. Hydrogen peroxide reacts with an acidified solution of potassium permanganate. So this would be when we go to predict the products. One thing I want to be clear on, fourth hour I know was a little sketchy, things you have to know and don't have to do for the test. So in redox reactions, you will either predict the products or you will balance the equation. I will not ask you to do both. So if you have to predict the products, you'll probably have to consider which one's oxidized and which one's reduced, but you won't have to worry about balancing it so their electrons are the same. You won't have to worry about balancing it so your atoms are the same. Does that make sense? They were a little unsure about that. So if you saw the most recent redox practice I gave you and I put online, I didn't balance those because I didn't expect you guys to balance. But I did identify what was being reduced and oxidized. Okay, so when we go to solve this problem, the first thing we're going to do is what? Let's write out our reactants. So what does hydrogen peroxide look like? Good. H2O2. I would probably, if this were a test, have said a solution of hydrogen peroxide. So what state of matter? That's probably bad. Hydrogen peroxide is a liquid. So we're going to just do that. Liquid hydrogen peroxide is what I would have said. Reacts with an acidified solution of potassium permanganate. So a couple clues that this is redox. What can you look at to know this is a redox reaction? So acidified solution, permanganate, hydrogen peroxide. Those are things that typically we're going to find in a redox reaction. So hydrogen peroxide, it's going to react with my potassium permanganate. So that's KMNO4. It's really important you have your polyatomic ions memorized, especially ones like permanganate and dichromate. You know those are going to be on your test because we've talked about them a billion times. So you want to have those memorized for sure. And then obviously, the more polyatomic ions you have memorized, the better your life will be, because then you will be more likely to come across the ones that are on the test. So that being said, I've predicted written my reactants. If this had said instead of an acidified solution, remember sometimes we would say like reacted in a solution of sulfuric acid or nitric acid is added to the solution or something like that. So those types of acids, not necessarily ones that are going to be reacting. Speaking of, I did tell fourth hour, I would recommend that you know HCl, HNO3, and H2SO4. If you don't know specifically how to name an acid, if you're still in that ballpark, I'd at least memorize HCl, HNO3, and H2SO4 as being hydrochloric acid, nitric acid, and sulfuric acid. Would recommend that you know those three. Those are the most likely to come up on the test if you don't know how to name an acid. Obviously, knowing how to name an acid would be preferable. Okay, so next up, what do we do? Okay, so we're going to predict our products. So a good thing to do to help us predict our products is I'm going to write the compounds out that the way they would be in solution. So it's Km, K plus, and then MnO4 minus. And of those guys, what one do you think we're most likely to look at first as far as, is there anything we know is likely to be oxidized or reduced? What's MnO4 minus likely to become? Okay, good. Mn2 plus. And so Mn2 plus for sure is going to happen. I don't have any hydrogens written in my reactant side, so it's kind of your call. We know that they're there. How do we know that they're there? Because it's in an acidic solution. So I know hydrogen ions exist, and so you can always add them in if you want to. And that helps you to recognize that the reason that that became +2 is because those oxygens were stripped away. When those oxygens get stripped away, they bond up with those extra hydrogens floating around, and they do make water. But it's more important to me that you know the Mn +2. I'm less concerned about the water. Okay, so then I've got a couple options, and I need to think about what's going to happen next. So a good thing to look at is what happened to my manganese right here. What was manganese's oxidation state here in O4 minus? +7. So we just did that on our FRQ, so you might have that in your brain. If not, I promise you'll have a question that asks, what's the oxidation state? So we know oxygen's typically -2. If there's 4 of them, this side's going to be a -8. And so since my overall charge is a -1, manganese has to be a +7 to get there. So oxidation states are for sure. If I go from +7 to +2, because remember, when there is a charge, that is its oxidation state, what did I do? Gain or lose electrons? Gain. If we gained electrons, then it's what? So I have reduction happening here. So I need somewhere oxidation to be happening. In order for oxidation to occur, what happens to my electrons? We're going to lose them. So my choices really are my K+ and my H2O2. K+, can it lose any more electrons? No, because think about potassium. It only had the 1 valence electron. In order to lose extra electrons, those are going to be coming from those core electrons in an already filled shell. So potassium's ions are never going to be involved in oxidation. Plus, we know they're an alkali metal. We know they're very soluble. They're not likely to react in any of the things we're going to deal with this unit. But both of those things are important things to recognize about why you can't get K +2 or K +3. That doesn't happen. Does that make sense? Okay, so then that leaves me with hydrogen peroxide. On your things you're supposed to know sheet that I had you memorize, we know hydrogen peroxide is likely to do one of two things. It's either going to become O2 and H+, or it's going to become water. And I said, I want you to know both of them. In one instance, it's being oxidized. In one instance, it's being reduced. So here on the hydrogen peroxide, what is oxygen's oxidation state? -1. Remember, hydrogen peroxide is the only time oxygen has a -1 charge. The whole rest of the time, it's always -2. So in this instance, it's -1. How about oxygen on this side? This one's 0 because it's diatomic oxygen. This is oxygen in its elemental state versus the water one down here. What's its charge? -2. That was kind of tricky what I just did there. I said all the rest of the time it's -2, and then I said, what's this one? And 0. That was mean of me. I didn't mean to do that. Sorry. But I do want you to recognize those are the 3 instances where oxygen can have different oxidation states. Elemental form, just like all atoms in their elemental form, have to be 0. Peroxide's -1. Other than those 2 instances, assume oxygen is -2. Fair enough? So which one of these is it losing the electron in? The top one. Here is my oxidation version, which means what's happening down here? Reduction. So hydrogen peroxide has the ability to do both. And so you have to choose the one that makes the most sense. In this particular problem, what's your hydrogen peroxide likely to do? Go to O2 and H2O. So I'm going to come up here and predict my products some more. I'm sorry, O2 and H+ is what I meant to say. O2 and H+. And so I'm going to go ahead and write those products in there is what I'm making in my reaction. I don't really want to erase this. So then I can show that my oxygens from here to here are being oxidized. And we can see overall you have somewhere reductions happening and somewhere oxidations happening. You always want to check that just to make sure you haven't done something crazy, because it's easy to do that. There's a lot to keep in your head for this. And then I'd encourage you to rewrite your products with anything that doesn't cancel out. So like K+, you know it didn't do anything, so we could write it on the other side. It's going to cancel out. It looks like we have H+ on both sides, so we probably don't need those in here. So I'm going to rewrite in orange here. I'm going to run out of space otherwise. And then you would stop. You don't have to balance it. You don't really have to tell me any other information. As far as predicted, that's all I would expect you to do if I've asked you what the products are. It's not balanced perfectly, and that's just going to be okay with us for right now. Later in the year, we'll learn how to balance it.
Why is there an H plus on the reactant side?
In the final product, I didn't put one in,
But why, like for that?
and we talked about there being one in there because that's how we formed our water.
Okay.
Okay, so if you are going to put water in here, then you should recognize that there is H plus over here. You don't have to do that. You could have done it without water, and then you would have not put H plus in there, and that would be fine too. Does that make sense to everybody? That's a good question. Okay. Yes, ma'am.
So, would that, because I'm so confused on what it is, that's not a net ionic equation?
This is a net ionic equation. This is a net ionic equation because it shows only the reactants and products literally involved in the reaction. I took out the H pluses because while they were doing work within the reaction, the beginning and the end, I had H pluses left. I took out my K pluses because they actually didn't do a lot of work in the reaction. They didn't do anything from the beginning to the end.
So on the test, we'll be writing all of our predicting products in the.
I would assume you write in net ionic equations.
Okay.
It would. But other than being something that allows permanganate to be in solution, K plus doesn't do anything else. So it's what we call the spectator ion. So it's not involved, but you can't, we can't just put ions into solution. Oh, I should have asked you before I erase this, but do you guys have any questions? I'm going to go over the ones that we need to have memorized.
For the MnO4 and that being an anionic, do you not break that apart because it's a polyatomic ion?
Yes, that's a great question. Any other questions about that?
What would the state of matter be for the Mn+2?
It would be aqueous. Anytime you have something that's written with a charge, thanks, I forgot to do states of matter on that side. Anything that you have written with a charge will always be aqueous. Because the only way you can get an ion is through it being aqueous. So then water typically is a liquid, but I think you can get away with it being either one. In this instance, it's going to be a liquid because you have it all in solution. Like in combustion reactions, it's very, very hot, so sometimes it's a gas. But water you'd call a liquid most of the time. Oxygen is a gas. You guys have my periodic table. It's got the colored on it. Remember, red means in its elemental state it's a gas. Black means its elemental state it's a solid. Yes, Joey?
I know you have freaking products up there, but we also cover like that problem. We have 2 beakers and we like tell which elements were in each beaker.
Yeah, I might come to that when we do the redox titration.
Okay.
We'll see how we're doing time-wise. But okay, so request for what do we have to have memorized? Okay, so this would be like chlorine, bromine, becomes Cl2, Br2. So these are the main things you need to have memorized. They started our notes we took a couple classes ago. Might have been a whole week ago now. That's what it said in the first slide. These are the ones you have to know. The idea that your halide ions are typically going to become chlorine or their diatomic halogens. So Cl minus becomes Cl2, Br minus becomes Br2. Dichromate is going to drop its oxygens and become chromium plus 3. Permanganate is going to drop its oxygens and become Mn plus 2. And then the 2 different instances for hydrogen peroxide. Those are the ones I'd like you to be familiar with for the test. Okay, and then I think I'm going to switch to redox titration if there's no other questions on predicting products. Can I get rid of this? Is there anybody that has a particular, did you have a particular redox titration problem?
I actually have a question, like going back to that.
Go for it.
When the permanganate is in a solution, it becomes like and then also becomes H2O. Does chromate do that same thing? Or
Dichromate, yeah.
it does.
Yep, it does. Because both of them only do that in an acidic solution. So those oxygens are grabbing onto the hydrogens and forming water. Yep. Okay, so redox titration, if we were just going to make one up, I mean, we could have used that reaction that we just did, the idea of your hydrogen peroxide reacting with potassium permanganate. That would probably be a good one. I'm trying to think of how I can word this. We'll do, okay, so we, okay, wait, before I say this, I want to pause here before I give you the rest of it. I want you to think about limiting reactants for a minute. So I'm obviously making this problem up as we go. But given a solution of 2.5 molarity sodium dichromate, determine the molarity of 100 milliliters of an iron 2 solution. Okay, I'm going to give you some more data in a second, but just based on that information, what are we trying to figure out? Molarity of iron. So what do we need to be the limiting reactant? Iron. And my excess reactant then would have to be my dichromate. Okay, so then in my lab, I'm going to give you some values. I'm making numbers up. 0.67 milliliters of, and this would have to be my dichromate solution, sodium dichromate. I'll want to write that. Okay. So if I were going to draw a flask and say beforehand, the flask is what I'm going to analyze. So this is my before. And then my flask after. What would be in my flask before? So if my flask is what I'm analyzing, then that's got to be the solution that I'm looking for. So what's my solution that I'm studying? My iron solution. So my iron is going to be what? Fe+2. I didn't tell you it was acidified, but I probably should have said something like acidified with nitric acid. So if we acidified it with nitric acid, we'd also want to put in H+ and NO3-, and they would need to be separate because HNO3 would dissolve in water, and it's an acid. Acids are always separated. And based on this information, in my analyte, I wouldn't have any other substances. So then I'm going to run my reaction, and what would happen after my reaction? I probably would give you a balanced equation for this, to be totally honest, but let's just see what you guys can come up with based on things we talked about this year. So probably it would form some water. That sounds like a solid guess. Probably going to make some CR3 because here my CR2O7 is going to be reacting with my Fe+2, and it's going to be forming some stuff, right? Cr+3 is one of them. What? it would form some sort of iron, but not probably iron oxide. What's it going to do to the iron? It's going to have to change its charge. Anything else that would need to be in there? Am I writing it too small? Cr plus 3, Fe plus 3, water. What'd you say?
NO3 minus.
NO3 minus, because that can't just go away. Should be at least one more thing that's for sure in there.
Why is there H plus on the before and not just water?
So because I told you here, in this one or this one, we don't need O2. We wouldn't make O2. The oxygen that's left would go to the water. We would for sure have Na though, because it was a solution of sodium dichromate. So as my dichromate was added, I definitely would put in Na. There should be at least one more ion in there. H plus is an optional one, but it's a good one to put in there. Why would I have to have Cr2O7 in here? Because I established up here that I want my iron to be in excess. I'm sorry, my iron to be limited, which means what I'm reacting it with has to be in excess. So I definitely want that in there as well.
So the reason that there's Cr3 plus and Cr2O7 is because the Cr3 plus is what reacted with the iron, and then
The Cr3 plus is what was formed.
is what was formed with it.
Yeah, so both of those products would be there for sure.
Okay.
And then because I established earlier, this is my limited reactant, that then in essence means this has to be my excess reactant.
Okay.
So if you have it as excess, you need to show it's in excess.
So that's H plus on the after side too, is that right?
And we put H plus on the after side because I said you can put it there or you cannot. That wouldn't be necessarily. H plus in water, you probably should have one or the other in there at least, but you're welcome to have both of them in there. Okay, I think that's everything you guys need. Okay, other questions about that? Yes, sir.
Since it's a titration, do you really want an excess of dichromate, or do you just want them to be like perfectly balanced?
Well, most of the time in your titrations, when you see that color change, most of the time when you have your color change occur, it's because you've put enough of your reactant in there to cause it to switch past to the other one. So most of the time that is like one little tiny bit extra of your excess, and that's how your sign is that you're switching. And that happens even in our acid-base reactions. So yeah, you would. Other questions about that? All right, if we wanted to solve this, I should have probably asked you before I erased it. Again, sorry, good thing we're recording. So what number would I start with? We've got a lot of numbers here. How come you're starting with your 45.67? Good, it's the one we know the molarity of. I love it, you guys are geniuses. Okay, so one of the things that I asked about is how we use molarity in a conversion. And so in my molarity, 25.5, that's not what I meant to say, 2.5 molarity is the same thing as 2.5 moles per 1 liter. So this is a difference, like a setup that means the same thing. So it's a way that I can use to convert from moles to liters or liters to moles. It's all the same thing. If we wanted to say like the same idea that 12 feet is, I don't know what that's equal to. 12 inches is equal to 1 foot. Those are conversions that are equal to each other. So when I say 2.5 molarity, that means I have 2.5 moles equal to 1 liter. So I could switch this just as easily and say 1 foot over 12 inches. It's equally the same to say 1 liter over 2.5 moles. This is just a tool that I can use in my charts as I need to set it up so that I can switch between the units that I want. Does that make sense? I could do that with anything that I have units of. Kilometers per second, miles per hour, Later on the year, we're going to do lots of different conversions, and we want to make sure we have those. So far, so good? Okay, so if I've got milliliters here of my dichromate, which really I only care about the dichromate part, so I'm just going to put that part in there. Because this isn't grams. If this were grams, it would have to be, I'd have to include the sodium dichromate, right? If this were grams of Na2Cr2O7, then I'd be measuring its mass. But in solution, my ions are separated. So I just am curious what's happening in the ions. And so it's okay to just focus on the ions. If you're in grams, you have to focus on the whole compound because that mass is going to be representative of how much sodium and how much dichromate, because this is before you put it in solution. Does that make sense?
Can you just like explain that again?
Sure. Okay, so you can, if you had grams of sodium dichromate, you have to start with grams of all sodium and dichromate because that solid, the only way dichromate can be there is if it's connected to a sodium. So they have to be together as a solid. If you have it in solution, they're going to have already separated. So it's perfectly fine to just look at the dichromate. So far, did that clarify everybody?
So does that mean for the molarity, you just write Cr2O7, or is it going to be NX?
I just wrote Cr2O7, but you could do either one. You would be okay either way. But I just wanted to focus on the one I was curious about. Okay, so I've got 45.67 milliliters of dichromate. And so my goal would be to turn it into what? Moles of dichromate. That's almost always the first thing I'm trying to switch between. So what do I know about my dichromate? 2.5 moles. I have 2.5 molarity of my Na2Cr2O7, right? So that means that's how many moles I have for every 1 liter. And so if you're thinking to yourself, well, if I just get rid of that sodium, you know, when they go to separate out, how many dichromates do I have in here? I just have 1 dichromate, right, in my set. So every time it dissolves, I still have 1 dichromate. So it's a 1-to-1 mole ratio. So however many moles I have in my solution, that's also how many moles I have of my dichromate, excuse me. So those of you that are feeling like, why can't I just get rid of the Na? That's just another thing for you. So I'm going to put my 2.5 moles up here, and I'm going to say 1,000 milliliters on the bottom, so I don't have to bother with rewriting what I wrote over there. So you guys, no.
It's hard to see the dot.
Sorry, that's a dot.
Oh.
That make it better? Yeah, it's 2.5 moles. Although I guess it doesn't really matter because I'm just making up numbers. I don't know what's going to happen. Okay, so we've got moles of dichromate. What do I do next?
Mole ratio.
Mole ratio. This would be a good moment to have a balanced equation. I didn't give you one of those. Oh, man. Cr2O7. So my chromium's here. I'm just going to tell you guys what I'm doing. So this would be a +6. And I have, so to go from +6 to +3, what am I doing? I'm reducing by how much? 3 electrons. But I have 2 chromiums here, and I have 2 chromiums here, so I have to double that number. So it's actually 6 electrons that are changing. You wouldn't have to do this, but because I'm doing it. So you know, from +2 to +3, what's happening there? And so since I'm trying to balance that with 6 electrons, I need to multiply this by 6. So I'm going to put a 6 here and a 6 here.
So hold on, how come you don't multiply the first CR07 as well? Because it's already has 6?
Right.
Okay.
It already had 6 transferring. So then I'm going to do 7 moles in here. 15 hydrogens. Okay. So let's just imagine that was a good practice for the balancing oxidation reduction part, but the second half, I didn't do it oxidation state method wise. So we've got some numbers here. So imagine I would have given you this balanced equation to start with. So then my next step would be I want to compare the mole ratio between what and what? Dichromate and iron. And so I used my molarity here in my conversion. So I've already converted to moles, but I'm in moles of dichromate. So I'm going to put that number down here on the bottom. And so I had no number in front, so I know it's a 1. And then for iron, it's a 6. So I'm going to say 6 moles of Fe plus 2. That gives me how many moles of Fe plus 2. Is that what I'm trying to solve for? I need to know my molarity. And molarity is what? Moles over liters. And so right now, if I were to solve this answer, my answer would be in what unit? Moles. Since I need it moles per liter, I just need my answer to be divided by liters. So I'm going to put down here how many liters I had in my reaction, which is how many. If you can see this tiny little writing right here says 100 milliliters. So it would be 0.1 liters. If you're not 100% sure about that, you could always put in your 100 milliliters on the bottom and then kind of help yourself to cancel it out and say, well, I know there's 1,000 milliliters in every 1 liter. If you're not sure about what to do for that. The other option is you could solve for moles and then just separately divide by liters. It's perfectly fine as well. Did you have a question? Oh, I thought you were sharing. Does that help? Redox? What other questions do we have about this? So if you were to go, oh, I should probably solve it. Does anybody want to solve the answer for me?
6.851.
Okay, that sure is a lot of significant figures. Say it again.
6.851.
Okay. Well, that's here we have 4 significant figures, which is awesome. However, here we have 2 significant figures. So we want to make sure we round our answer. I heard up here. Is that you? Thanks so much. 6.9 is my molarity of my Fe plus 2 solution. So this would be a good instance where if I were going to take points off for significant figures, then this is where you would lose that point. Typically it's done in subtraction, but this unit we don't always have subtraction. Okay, questions on redox titration-y stuff? So far, so good?
Would this type of thing be an FRQ question?
This would be a good FRQ question. Your FRQ question will either be about a redox titration or about a gravimetric analysis. Those were our 2 big labs that we did, so that's going to be what your FRQ is about. And I'll try to use concepts from each lab, kind of like you saw in this practice FRQ. We talked a lot about why limiting reactants kind of work they are in the gravimetric lab, but I asked you about that in a redox type lab on this most recent FRQ. Okay, so I feel like we kind of talked about the molarity solution. Are you guys feeling okay about that? And redox we're okay with. And then we have limiting reactant we did okay with. Do you want to work out some net ionic equations with about 5 minutes left? Yes, does that sound like a good plan, or is there anybody who wants to do anything else? Okay, Kelsey, go for it.
So when it comes to limiting reactants, what are we supposed to be able to do with those on the test?
You should be able to conceptually tell me which one's the limiting reactant, and you should be able to mathematically calculate which one's the limiting reactant. Are you wanting to calculate a limiting reactant type problem?
Yes.
Okay.
Will there be empirical and molecular formulas?
Yes. For sure is fair game. You had one on your AFL.
Yeah.
Yeah, I'm trying to think of a limiting reactant problem here. So like for limiting reactants, are you just looking for how to solve one? Like the general process, is that what you're looking for? Yeah.
Yes.
How many people would rather see a limiting reactant versus net ionic equation? Those are your choices. How many people want to see limiting reactant? How many people want to see net ionic? Okay. Limiting reactants is the winner. Okay, so let's say I were to just make up a reaction. This is just an easy one to use. So if I were to use that, is this a good instance to use molarity, or do you like it when it's in grams, or do you care? Okay. vote is what are we at? So if you had a reaction in that you were trying to determine the limiting reactant through calculation, you would have to know exactly how much you have of both reactants. Since these are gases, I kind of have to do grams. But so let's say we reacted 15 grams. Oh, I think we did 5 grams of hydrogen, and we reacted 5 grams of oxygen. And so the question is then, how much water can you form? We'll do how many grams? How many grams of water? So if I wanted to do this reaction, there's 2 ways we can solve for limiting reactants. We can start 2 different T-charts with each of my reactants, or we can solve one chart and figure out how many grams does it take to react with the other one. That's the way I showed you in class. The 2 different T-chart method is the one we did in General Chem. I was thinking about showing you the 2 different General Chem ones just because that's a little different than we did in class, unless you'd rather go from 1 gram to the other gram. What'd you say? No, I won't ask you a specific way. You can do it either way. How about, since it seems like we're not 100% sure, I'm going to go from 1 gram to the other. And 4th hour, I did solve both of them and calculate the smallest. So you can watch the video for that one. So if I have 5 grams of H2, I need to go from grams of H2 to figure out how many grams of oxygen. So that would be 2 grams of H2 for every 1 mole of H2. And then according to my balanced equation, it's 2 moles of H2 to react with 1 mole of oxygen. Oops. 2 moles of H2 for every 1 mole of oxygen. Have I lost anybody at these points? I went from grams to moles and then moles to moles. Okay, and then I'm going to go from 1 mole of oxygen to 32 grams of oxygen, because remember, oxygen is diatomic, each one's 16, and that's what I get. Okay, so let's calculate that for me real quick and tell me what we get. 40. Okay, so 40 grams of oxygen is how much oxygen it would take to react with 5 grams of H2. Do I have 40 grams of oxygen? So which one is going to run out first? My oxygen. So my limiting reactant would be oxygen. So then I'm going to start my next reaction with how many grams of oxygen, and I would take my grams of oxygen and turn it into grams of water. And so it's 1 mole of O2 becomes 2 moles of H2O, and then 1 mole of H2O is 18 grams. Okay. Stop by if you need. No, you're fine. Stop by if you want your lab reports back anytime that works for you that I'm here. And otherwise,